All right, class, welcome back. So this is an explanation video for handout number 27, questions 3 and 4. If you're not in my class, then this is just a precipitation problem that's going to show us how to do molecular equations, ionic equations, net ionic equations, and then also for us to think about doing gravimetric analysis, doing practice problems that involve our precipitation reactions. So let's go ahead and get started with this. The first thing that I would do is for this question number 3 is I would sort of read through and pull out the relevant information. We're asked to find molecular, ionic, and net ionic equations. These are the questions that we're supposed to answer. I might write, molecular first over here. That's going to be number 1. Then we'll do the other ones from there. And we're going to react together aqueous solutions, so that means water-based. So lead nitrate dissolved in water, that's aqueous. Lead nitrate and potassium chloride, we're going to mix those together and then see what happens. So I would first then write out, what lead nitrate is going to be. That's going to be PbNO3 aqueous. That means that it's dissolved in water. So, sort of two reasons there that I'm going to write this out. Number 1, I know that it says aqueous right here, so that suggests that it's dissolved in water. The fact that I see nitrate, so whenever I see nitrate, I know, I've used my solubility rules, my tables, enough that I know that nitrates are always going to be soluble. You might not be at that level yet. The more you practice, the more comfortable you'll get with that idea. So lead nitrate, and then of course, because lead is a +2 ion in this case, then I'm going to need 2 of these nitrate polyatomic ions to balance that out, right? It's an ionic compound. I've got to have an overall neutral charge, so lead +2, 2 nitrates. Nitrate is a -1 ion, so I'm going to need 2 of those. So this is the first piece. Potassium chloride. Potassium is K, Cl, again, that's going to be aqueous. If I see potassium, I know that's in group 1. Group 1 ionic compounds are always soluble, so that's going to be my other reactant. So these are going to react together, and I need to now predict what my products are going to be. So this is a little confusing, especially when you're first starting out with these, but basically what I'm going to do is I'm going to take the cation from one species, and I'm going to pair that up with the anion from the other species. So cation here paired up with the, so basically I'm just going to switch partners. So the lead I'm going to write as matching up with the chlorine, or chloride, I guess I should say. And then I can use my solubility rules to figure out that this lead chloride is actually going to be insoluble. It's going to form a precipitate. It's going to be a solid product. So that's going to be my product. For the other pieces, I want to make sure it's a balanced chemical reaction. I'm going to pair up the potassium with the nitrate. That's just going to be KNO3. Potassium is a +1 ion. Nitrate is a -1 ion, so I just need KNO3. I need to make sure that I balance my chemical reaction. So to balance this, I'm going to need a 2 here and a 2 here. I guess the way that I thought about that, since we were over here with the nitrate anyhow, I know that I've got 2 nitrates over here. I'm going to balance that with a 2 here. Then I need to balance my potassiums, 2 potassiums here, 2 potassiums here, and then my chlorides that's going to make my chlorides balance out. So this is my balanced molecular equation. Make sure we've got all of our relevant phase labels: aqueous, aqueous, solid, and aqueous. And again, I know that this is a solid because of my solubility rules. I can look up that, chlorides are typically soluble, but then lead's going to be an exception there. So this is going to be an insoluble precipitate. So that's my molecular. For my ionic, we really need to have a good understanding of what this aqueous means. Basically what that means is it means it's dissolved in water. So I could actually, when I see this, in my mind, what I'm actually seeing is that the lead 2 is dissociated into ions, and then I'm going to have 2 nitrate ions for every one of these lead nitrates, right? This is going to dissociate into 1 lead 2+, and then 2 NO3- ions. So I'm going to write all of my ions out. K plus aqueous plus 2 Cl- aqueous, right? These 2 coefficients come from the fact that in my balanced molecular equation, I've got 2 KCl, so that means I've got 2 equivalents, so 2 K plus and 2 Cl- total. Those are all going to be aqueous, so initially I've got all of these ions there. The lead chloride is going to be a solid, so it's going to stay as a solid. We're not going to break it into ions because it's a solid. It's not breaking into ions. It's actually come together. Plus 2 K plus aqueous, and we're just going to fit this in, 2NO3 minus aqueous. So that is my ionic equation. It's going to show all of the different ionic species written out. And this is, this is really what we should be seeing in our minds when we read this molecular equation. When I see this molecular equation, well, this is, showing what's actually going on. So it's really a better way to think about a molecular equation like this. But the molecular equation is just, it has all the same information. It's just a little bit more convenient to use. That's why we use it much more often. The net ionic equation I'm going to go through, and I'm going to cancel out any ions that show up on both sides. So my NO3 shows up on both sides. That's what we call a spectator ion. So we can actually put that in here, spectator ions. So we can go ahead and cancel those out from both sides. They're not participating in any chemical reaction, any net chemical reaction. Our net chemical reaction is just going to show us overall, what is changing in my chemical reaction. So what's changing is that these lead 2+ and chloride 1- ions are going to come together to form this new lead chloride precipitate, which is going to be a solid. So that is my net ionic equation. So this is going to be useful information, just to sort of show us what's actually happening. All right, let's go ahead and do this question number 4. So in question number 4, we're going to utilize really our molecular equation. We could use our ionic equation or our net ionic equation, but in my mind, most often the things we're going to be working with are going to be these molecular equations. So I think it makes most sense to just go back and sort of use that. I forgot my phase label there. PbCl2 solid plus 2KNO3 aqueous. So here's our molecular equation, and this is what we're going to be using most often. I think it makes the most sense when we're doing a limiting reactant or a theoretical yield type problem. Just go back to your molecular equation. It's gonna make the most sense for the things that we've been doing so far. So in this problem, we've got 1.23 moles of lead nitrate and 1.34 moles of the KCl. We're going to need to figure out what the limiting reactant is, and in this case, this KCl is actually limiting. So I can recognize that basically because I can see that's a 1-to-2 ratio. That's why balancing our chemical reactions is very important. So our ratio is 1 lead nitrate for every 2 KCl's, so we're going to be consuming the KCl twice as fast basically. So if I've got roughly the same amount, well, this one's going to run out faster because I'm using it at a 1-to-2 ratio. I could actually show some calculations there, and if you're unfamiliar with how to do limiting reactant problems, definitely make sure you spend some time brushing up on that, learning how to do that. But I know that this KCl is going to be limiting, so I'm just going to move ahead with that. So now that I know that KCl is limiting and I want to find the mass of precipitate, that's going to be the mass of this lead chloride. So I need to figure out how many moles of lead chloride will be formed. So 1.34 moles of my limiting reactant, which is KCl, times 1 mole, using my mole-to-mole conversion here, for 1 mole of lead chloride is going to be formed every time 2 moles of KCl are consumed. That means that I'm going to produce 0.67 moles of lead chloride. And then the last step is just going to be to convert this moles of lead chloride into grams of lead chloride. Hopefully at this stage we can definitely do that. So to do that, that's just going to end up giving us 186 grams of lead chloride. So molar mass of lead chloride is 278.1. So just this 0.67 times 278.1, our units of mole should cancel, gives us this units of grams of lead chloride. That's what we're looking for this problem. So hopefully this makes sense. This is just a very basic molecular ionic, net ionic, limiting reactant type problem. We might also call this gravimetric analysis, but all of that sort of makes sense and lead us to this final answer. All right.